get started. So I apologize, I'm a little sick today, but tested negative for COVID, so we're here. So I apologize if my voice is messed up. Up at the front, I have your homework and then the lab as well, so you can pick that up. And then I'm a little behind on grading, but you should at least get the quiz 1 back from me. I think I'm missing a few people, or / people are missing. So you should get that back from me. And then otherwise, I'm just continuing to grade. And then I posted the previous notes on Blackboard. Did everybody find those if they look for them? And so I post them in both the OneNote and PDF format. Any other questions before we dive into Chapter 3 here? And then, so don't forget, we're doing flame tests. So I saw some people in lab today, but if you didn't have lab on Wednesday, try to wear your cotton clothing and no holey pants and just be ready for flame tests. And probably a hair tie, but I brought some hair ties for y'all. All right, so let's dive into Chapter 3. Oh, quick random survey. Is anybody in biology 211 by any chance? I was just curious. All right, disregard. All right, so let's go into chemical bonds. And so this is just really basic. First we're saying, well, any sort of compound is composed of atoms held together by chemical bonds. And here, this is just vague. So later we'll go into it, but this means both, right, ionic and covalent. And we'll learn, well, what the heck does that even mean? And so chemical bonds can either result from the attractions then between your charged particles. And so this would be from an ionic bond where you have opposite charges. And then we'll also look at kind of sharing electrons, and that makes your covalent bond. And so then we have our 3 main types. So we have ionic, covalent, which we'll mainly be focusing on. And then I included metallic under here, but we're not really going to talk about it. So metallic bonding is a little different. And so it can usually be kind of simplified as like a sea of electrons. But again, in this class, we're not going to get into that. So this kind of goes into like why metals are conductive and blah, blah, blah. But we're going to mainly focus on ionic and covalent. So if you want to highlight that, like this is our focus in this class. And so then we want to be able to make the distinction of an ionic versus a covalent bond. And so this is kind of like your classic example. And so they give us this table salt. And so notice, appreciate the difference. So this is a crystal lattice structure. And right, this is just more of your molecules. And so you can appreciate the difference. So the ionic compound, right, we don't just find one sodium and one chlorine ion together. They make this whole what's called the crystal lattice structure. So they form in this repeating pattern. And so they're in a 1-to-1 ratio, but you can have different what's called packing and geometries based upon the different atoms and then also their charges. But again, what we're taking away is it's not just some discrete molecules. They're, again, repeating units in the structure. And then the other key is that they're held together by these charges. So they have, right, electrostatic forces that keep them together just because we have opposite charges. So, of course, sodium is positive and chlorine is negative. And so we'll dive deeper into this. But we want to be able to compare that to the covalent bond. And so notice, right, all these molecules are drawn as discrete structures. So we can draw one individual water molecule that's appropriate. And then again, we'll look at how they share electrons. So this is kind of going back into our Lewis dot structure a little, so kind of peeking in there, it's like we have oxygen, 6 valence electrons, hydrogen with 1 valence, and they're going to end up making a bond like that. So each of them contributing 1 electron to that bond. And again, we'll go in more depth as we march through the course. So then let's focus on our ionic bonds. And so this occurs between our metal and our non-metal. And let's see if do I have a periodic table? So again, right, you're looking at opposite sides of the periodic table. So we focus a lot on group 1 and group 2, plus any of these non-metals, but you could also have, right, your transition metals paired with a non-metal. And again, the key is they involve a transfer of electrons from one atom to another. And so I'll put, so again, it's usually group 1 and 2 focus, and then I'll put under there our transition metals. And so you've maybe gotten a little taste of this with the homework. And so we kind of mentioned before, we have our ions, right, our charged particles. And so usually what happens is the metal tends to supply the electrons. And so the metal becomes a cation. And so, right, it loses electrons, so it becomes positive. So you can put a big positive charge there. And then the nonmetal becomes the anion. So remember, that's negatively charged. And so let's look at sodium chloride. But before we look at it, so let's kind of recap what we were learning. And we also want to put it in context of everything. So can you write the electron configuration for both sodium and chlorine? So just start with that. And do we have Ava or Ashley here today? Do we have sodium's electron configuration? Do we need more time? I'll give people another minute or so. So somebody give me sodium's electron configuration. So 3s1, but let's put in the noble gas. Yeah, that's an easy fix there. So neon, so we start with neon, and then 3s1. And this is kind of nice that we've written it out this way, because now we can clearly see we have one valence electron. And again, this should match. So at some point, maybe you wrote there's 1, 2, 3, 4, 5, 6, 7 valence electrons, right, all the way across the periodic table. So we're kind of both reaffirming this, right? 1 valence electron, 2. So hopefully you have this written, or again, remind yourself this corresponds to these little group numbers here. That also helps you. And so let's also write the Lewis dot structure. So what would the Lewis dot structure look like for sodium? So it has 1 valence electron, right? What would it look like? Yeah, so just an Na with a dot, and it doesn't matter where you put the dot. You could put it on any side. But this is good. All right, so now let's do chlorine. Are we ready for chlorine? Or all right, give it to me.
So neon in the brackets, and then 3s2, 3p5.
So that looks good here. And again, so we can clearly see we have our valence electrons. And so we could translate this to our Lewis dot structure as well. And so I'm going to fill it up 2 in the S first, and then go around to fill up my P. So I get something like that, right? And so now this is giving us a hint of what's going to happen. So in this reaction, we said, well, sodium is going to donate. And so that's exactly what's going to happen, right? This electron is going to go over to chlorine. And we can see that. And so now we can rewrite this. And so something to practice. So now can we write our electron configuration of sodium plus and then chlorine negative. So take a minute or so for that. So what do we get for sodium plus? What's its electron configuration? And we could base it off of this one. So what is it? Brittany, what do we get? Or not Brittany. Bethany, sorry. So what do we start here? So we're looking at this, right? And then, so it was neutral. We just lost an electron. So what do we need to just write here? Because we're trying to show which electron was lost, right? Well, it'd be 3s0 technically, so we don't even need to write that. So we could just simplify it to neon, right? And we're just trying to show that this little electron left, right? And this is also kind of telling us reactivity. And so we're saying, okay, well, sodium, right, they're pretty reactive, one valence electron, it's going to give up that electron, and then it leaves us with neon's electron configuration. And so sodium now is happy by the octet rule. So it's satisfied. And then what's chlorine's new electron configuration, or new chloride? Yeah, do you have it?
Would it be neon in the brackets, and then 3 is 3 and
3s. So instead of putting it in the s, where do we put it though? Because the s can only have 2.
3 is 2 and 3 is 6.
Yeah. And so now this, right? Now it's also satisfied by the octet rule. So that's showing why this is favorable to happen, right? So now sodium satisfied by the octet rule. It has a filled orbitals, so there's no lone electron hanging out. And now this is filled by the octet rule. And so we can also rewrite now its new Lewis dot structures. And so you can write sodium plus. Usually you just show no valence electrons. If you wrote sodium plus, this is okay, but not really as good. Yeah.
So when sodium lost electron, it went to neon, and chlorine gained one, and it didn't go to argon.
Well, it would. I just didn't write argon.
Okay.
Yeah, so then we could put a parentheses, right, argon, and so it's basically argon.
Wait, so if it's negative, it adds an electron?
Yep, so remember, right, electrons are negative, so when it's negative, you're adding an electron. Yeah, that's always kind of confusing in your brain. That's why I always say, right, charge is proton plus electron, but electron is negative, so keep that in mind. And then for chlorine, though, when we write the electron or the Lewis dot structure, you do want to show that it has, right, 8 electrons now. And again, good observation in noting it's isoelectronic to argon. Questions about this? And so we see, right, these oppositely charged ions, then that is what holds together the ionic bond. And so notice, right, again, they're just held together by those electrostatic forces. So there's no physical bond between them. There's no electrons sharing between them. It's just the electrostatic charge. And of course, again, something to note is, right, you take 2 highly toxic things and then they make table salt. So again, sodium metal is nice and shiny here, and obviously you wouldn't want to eat it. That would just start reacting with you and forming base. That would be horrible. And again, right, it loses our electron. And meanwhile, we added chlorine gas, so again, super nasty to work with. And it becomes chloride, again, making our table salt. And so this is now just going into kind of Lewis dot symbols. And this is why I've been introducing it, you know, as we do our electron configuration. And so we'll just keep practicing that. And so you want to be able to write the electron configuration for the neutral, so we practice that. But then being able to see, okay, well, this is, right, my valence electron in potassium. And so when it becomes a cation, it's going to be losing that electron from the S. And so there they did write 4s0. Again, we usually don't do that, and you would just write a 3s2, 3p6. And so this chart is just supposed to kind of help you figure out which ions have regular charges. So again, this is just your group 1 with the +1, because they have, again, that 1 valence electron. Then our alkaline earth, again, they have 2 valence electrons. And I'll write some Lewis dot structures, so lithium. And so you might see discrepancies in group 2. So I would write it like this because we want to reflect that this is, right, an S block. But I know if you look at other textbooks, sometimes you'll find it where they put a dot on each side, kind of with that elementary candy rule method. But I don't really like this because it doesn't reflect the reactivity. And so I think this is better, right, because it actually shows that we have 2 electrons in our s orbital. So that's my only criticism of that. And then it shows scandium and yttrium. So these are usually 3+ oxidation state. So you can maybe mark that down in your periodic table that these are always 3+. And so that's significant since most of these transition metals have all sorts of oxidation states. We should also put there zinc. So zinc is always 2+. And for our purposes, silver is always 1+. And then aluminum is 3+. And then, of course, showing, again, our halogens. And we can write both our Lewis dot structure to help us. So I'm kind of drawing, right, the same information in different forms so it all starts to connect. And so something else that we'll do experimentally is we'll figure out that ionic compounds are conductive. And so that's because they have, right, a cation and anion. So if you put them in solution, now you have ions floating around that can make electricity run through them. So we'll test this out in lab. And so we haven't quite gotten there. I have to see how much this chapter covers. But I probably will have to give you a polyatomic sheet. And again, so we haven't gotten there. But these are some basic ionic compounds. And then when you see something like this, so this looks kind of weird. But what this is we have magnesium and a 2+, and then this sulfate, we'll later learn, is called a polyatomic ion. And so these are all covalently held together, but then it overall has a charge. So then it would look something like this, and I have to, oops. Let's see, so then, so this is what sulfate looks like. So sulfur attached to a bunch of oxygens. And so, right, magnesium sulfate, oops, is just that magnesium and that sulfate, again, the ionic compound. So here's just magnesium sulfate, although they showed the hexahydrate version. So in this case, water is just complex 2 magnesium. That gives you an idea of, again, what's going on. So they're still held together by those electrostatic potential formulas. And so when we write our ionic compound formulas, we're really writing the formula unit. So it's just the smallest electrically neutral collection of ions. And so all we mean by that is we have to balance the charges. So sodium is 1+, chlorine is -1, so they're written in this 1-to-1 ratio. If we were to write, so let's say we want to write the formula between magnesium and fluorine. And so in this case, right, magnesium is usually in a 2+ oxidation state. Fluorine tends to gain 1 electron. And so when we write the formula, we have to write 2 fluorines to balance that magnesium. All right, so let's look at how to name and write formulas. And so we'll start with ionic compounds. And so like I mentioned, there's two types of ionic compounds. So we have our metal that only forms one type of ion. And so again, and it lists them here, but that's group 1, group 2, and then it lists the other exceptions. So you have zinc, aluminum, and silver. And so with this one, we can just name them. And we'll look at how to name them. And then any metal that forms more than one type of ion, we'll have to name it slightly differently, and we'll look at that. But basically, we'll add, or let me say use, Roman numerals to denote the oxidation state. And so again, that's mainly your transition metals. And then some of your other weird exceptions are going to be tin. So tin can either be 2+ or 4+. You have thallium. So thallium's either 1+ or 3+. And lead, 2+, 4+. So generally those are going to be ones you'll see. And so how you name them is you just list your metal. So for our not variable oxidation state, so we just have our metal and then plus our non-metal, right? But then we change the ending of our non-metal to "-ide". So I'll do the first one. Actually, let's do a different one. Let's do this one. So we have sodium nitride. So in this one, right, we want to name the metal, so sodium. And then we take our non-metal, so nitrogen, but then we add the "-ide" to it, so nitride. So now take a minute or two to name these ones. All right. What do we get for NaCl?
Sodium chloride.
So sodium chloride. What do we get for MgO?
Magnesium oxide.
Magnesium oxide. What about CaF2?
Calcium
Calcium
chloride.
fluoride. Then the last one,
Aluminum oxide.
aluminum oxide. So that looks pretty good. All right, let's look at how to go the opposite way for a second. So what happens if we want to write our formulas? And so there's a couple of tricks. So let's actually look back at aluminum oxide. So aluminum oxide. So now let's go the opposite way. How do they get their formula? And so the easiest way to do this is kind of the swap trick, I call it. And so how you do that, so let's just say, okay, I want to write the formula for aluminum oxide. So I'll write aluminum and my O. And then so we know aluminum is 3+ for the charge, right? So we know that from our periodic table. And then oxygen is 2-. And so, right, if we were to write out the algebra, so in this case, we're looking for a neutral compound. So we could write out, well, 0 is equal to, right, our 3+, so our charge of our aluminum times X. So write number of aluminums plus -2 times Y, right, number of oxygens. But that gets a little burdensome. And all we really want to do, right, is solve for X. And so it turns out if you swap these values, that's the easiest solution. And so what I usually do is just this swap trick. So then this 2 becomes our little subscript for aluminum, and then this 3 becomes the subscript for oxygen. So that's where you do the swap. So that solves the algebra. And then you want to rewrite it, so Al2O3, right? And then you can always do a little sanity check. So I have aluminum, I have 2 of them. So 2 times 3, okay, that's +6 plus 3 times -2, so that's -6. So yes, I get back to my 0. So let's try that with another one. So see if you can give me the formula for strontium phosphide. How would you write that out? What do we or walk me through what we did. So what's the charge for strontium? What's its oxidation state? So 2 plus, so I'll start off, right, with the little 2 here, and then phosphide, what's that?
Phosphorus.
So phosphorus, and then what's the oxidation state? So -3. So the easiest thing, right, we could just do our swap trick. And so that gives us SR3, P2. And again, right, do a little sanity check. So strontium, we said 2. So 2 times 3 is +6. And then +2 times -3, so that's -6. So yep, we're back to neutral there. How does that feel? Does that feel okay? Make sense to people? Yeah.
When there's multiple oxidation states listed, do we typically shoot for the bottom one, or, because phosphorus had +5, +3, and -3?
So usually, so it gets weird because with those different oxidation states for phosphorus, that usually depends more when it's like bonding with other people. But if we're just doing like metal plus non-metal, usually you want to go for the -1 on phosphorus. But so if you have like strontium, phosphorus, and some other element, so usually we don't work with that, or because there are different rules, because like it depends what you're looking at, because sometimes we could still kind of figure it out if it's an organic compound, but then we might have like a wrong answer because we're just taking an average and not looking at the structure. Yeah. And then if other cases, it would be like a polyatomic, and in which case you would just take the charge of that whole like polyatomic. But we haven't like quite gotten to polyatomics, but we're probably kind of dancing around them. Yeah. So I just multiplied, so strontium is usually 2 plus, there are 3, so 2 times 3 gives me 6 there. And then phosphorus, right, 2 times -3 is -6, so this was just a sanity check that yes, it was 0.
So you just took the 2 plus and the 3 negative and then flipped them?
Well, yeah, so I flipped them to solve for the algebra, but then I just rechecked it because, right, they have to be neutral. So you have to have 3 strontiums to balance out those 2 phosphorus. Yeah, and let's just say, so right, again, we're kind of getting to polyatomics, but not really. And I just want to do an example to address your question about what if there's multiple elements. But that would just be, we'll start to recognize our polyatomics once I give you a sheet. So in this case, this is called nitrate. And this just is what it is, right? It's nitrogen. We can draw it out. So it looks something like this. So this is all covalently bonded. And then let's say we wanted to, let's just say, write the formula for magnesium and nitrate. So again, we would do kind of the same sort of concept. So magnesium is 2 plus, but then we're just looking at the whole polyatomic as -1, and then we can still use our swap trick then to balance it out. So 2 there, and then that just becomes a 1. So magnesium nitrate.
So in that case, you're just dealing with the nitrate as a whole, like, as opposed to.
Yeah, yeah, so you're just treating it as a whole -1 and kind of, it's usually best to kind of keep it as 1 unit, but again, we'll kind of get there and you'll see what happens. All right, let's keep at least marching forward, and we'll keep doing practice. And so now what happens if we have our multivalent metals, and then of course we need to go back to your question of, well, how do we write the formulas? How do we know what oxidation state is in? So then we'll get to that. And so metals in this category, of course, have multiple charges. And so again, their charge cannot be predicted and it has to be noted in their name. And so again, it mentions some of our exceptions, so lead, thallium, and tin. Watch out for those. And so what's kind of nice is we use a simplified naming system now. And so I showed the old naming system. So it used to be, even when I learned chemistry, we had this old naming system. And so let's just at least appreciate it in case you come across it, but then we'll go through how we name it. So if we look at chromium, so chromium has two main oxidation states. And so the old style naming is the lower oxidation state gets this weird -ose ending, and the higher oxidation gets the -ig. But lucky for you, you don't have to worry about all that. So instead, we've switched over to this Roman numeral method, where all we need to do is write the oxidation state in the Roman numerals. So we have chromium 2+, and so then we just write chromium 2. So a lot easier than, well, is it chromos, chromic, blah, whatever. Don't have to worry about that. So the same thing for iron. So we have generally iron 2 or iron 3, and we just note that with the little parentheses and Roman numeral. And so we'll just skip over to tin. So tin, we have a 2+ and a 4+ oxidation state. Again, we can just note that in parentheses. And so then we can write our formulas. And so, right, we have two different copper oxides. And so we have, and this could be tricky. And so again, right, make a star, make a note somewhere that the Roman numeral is the oxidation state. So sometimes, right, people look at this Cu2O and they write, oh, it's copper 2. No, right? This has to tell us the oxidation state, not how many that there are. So just write that note. And so again, we'll name it just like we did before, except we'll add our charge in our Roman numeral. And so here, right, again, appreciate how we can go backwards and forwards between these two. So if we just have this, right, Cu, let me rewrite this. So let's just say we're given Cu2O here, right? You could do your swap trick to still back out. So this is a 1. So now I say, like, let's reverse the swap trick and see if this holds. And so we get copper 1+, oxygen 2-. So this swap trick doesn't always work. We'll look at a few weird scenarios, but most of the times it does. And so where you want to check it is you want to check, does this oxidation state match? So is oxygen really -2? Yes, so this is okay. And again, now we get copper 1 oxide back out again from this 1 here. So copper 1 oxide. Right now we can go the other way. Well, what if I want to write the formula? So copper, and again, I'll use my swap trick. So it's 1+ here. Oxygen is -2 always. Do my swap trick. So 1 and 2, right? So we get back out our formula. So same thing now. So now copper 2 oxide. So now we can tell, right, they're in a 1-to-1 ratio. And so, right, this is already one scenario where the swap trick fails, but let's look at how we can correct that. So we have this CuO, right? Well, what happens when we back out our swap trick? Well, we get 1- and 1+, right? But the red flag there is oxygen needs to be -2, right? So that doesn't match. But if we get this case, then we can just multiply everything by the factor that we need. So if oxygen needs to be -2, let's multiply everything by 2. And so that gives us Cu2 plus, oxygen 2 minus. Oh, yes, that's still right, 1-to-1 ratio. They balance out. And so we can go forwards and backwards again. Does that make sense? Everybody's still with me? All right, let's do some practice then. So take a few minutes to go through these examples and write out the name then. So you might have to determine some oxidation states. What do we get for this one, FeCl2? Gracie, let's hear from your corner. What'd y'all get? So remember your swap trick, right? Or just think of the algebra. So what oxidation state is chlorine usually? So -1. And so we kind of have to use both our swap trick and also our charge balancing. So if chlorine is -1, what does iron have to be? 2, so we can do iron 2 chloride. And again, we'll be really explicit here. Oops. And so we can see reverse swap trick works pretty well. So I'll put a 1 here. And so again, let's back it out. So then that gives us a 1 there and a 2 for iron. And then again, just double check yourself. Is chlorine -1? Yes, that's what my periodic table says. And then it matches all up. So that works nicely. Then what do we get for this next one? I'll show this one. So what do we get for FeCl3?
Would it be iron 3 chloride?
Yep, so now iron 3 chloride, exactly. And again, right, double check yourself. You know, chlorine is -1. You could do the reverse swap trick. It works nicely here. So I'll put my 1 there, right, back it out. So this should be a 3+. This is -1. Yep, that matches. So that looks good. So this is one where if we're not careful, our swap trick will fail, but we can fix it. So what do we get for this one? Any guesses or? So 10-2, this would be a good guess, but I'm sure this is how you got here. So did you do the reverse swap trick? So you do, right, 10-2+, but then what's the problem with oxygen? So we do the reverse, right? We get this 2 to -1, but what's the oxidation state of oxygen? So it's 2, but then that's fine. So let's just multiply everything by 2 now, so we get everything in the correct ratios. And so now I'll just kind of rewrite this. So right, this should be 10-4, and oxygen 2- now. So this balances charge-wise. And again, you can double check yourself. So -2 times 2, that's -4 plus 4, so we're back at 0. Yeah, that's a little trickier. So 10-4 oxide. So the 10s, this is where, again, we saw that swap trick fail, but just double check yourself, right? Compare oxygen so you get the right answer. Or, you know, another way to set it up, you could use our algebra. So, right, 0 is equal to whatever the oxidation state of 10 is. I'll just use Sn as my variable, plus we know oxygen is always -2. And then there's 2 of them, so we could have set up the algebra and found our answer that way. Questions about this one? So this was tricky since we had to watch the swap trick. And then what about this last one? What's the name of this?
Cobalt nitrate.
So we need a Roman numeral though, so cobalt something, and then it should be nitride. So watch that "ide" ending. And then what do we need? What's the Roman numeral? But what's nitrogen's oxidation state? Yeah, so if nitrogen is -3, what does cobalt have to be? So +3. So again, this is another one where the swap trick kind of fails us, but again, we can fix it. So this gives us 1 and 1, so we know they're in a 1-to-1 ratio, but then we have to look, whoops, nitrogen is not -1, right? It's -3, so I need to multiply this whole thing by 3, and that works out nicely. Questions on that? Oops, so clearly I should have printed out a polyatomic sheet today. So I'll bring that for Wednesday. And so we'll keep doing practice. So polyatomics, again, I need to hand you one of these sheets. That will be much more useful. Maybe I'll try to run and print one while you do this. But basically what we do now, right, is we can treat this whole thing as one thing. So I'll point out a couple of ions we use a lot. So hydroxide comes up a lot. So we've seen that in lab. So either sodium hydroxide, where they're in a 1-to-1 ratio, so right, sodium's 1+, or if we have magnesium hydroxide, that would be written like that. Acetate, this one comes up a lot, and it always confuses students, including my 200 level, because it can be written as 2 different ways. So this C2H3O2, but it also could be written like that. And so this is what acetate looks like written out. So that's why it looks funny. So sometimes people write it as a COO to kind of show you it's a carboxylic acid structure, but, and yeah, so just watch out for acetate. Nitrate comes up a lot. So we use a lot of nitrate salts in lab. And so notice, right, you have nitrite versus nitrate. Again, just the oxygen. So nitrite just has 1 less oxygen than the nitrate. And you could draw out, you know, the polyatomic for it, but we'll get there later where we're writing polyatomic structures. And so you have this, all the chlorites and eights. So if you have a hypochlorite, that's like the least number of oxygens with this ClO negative. And then notice any perchlorates, that has extra oxygens, so that's 4. You don't really see that too much. Peroxide, so this is the only weird exception. So I've gone on and on and on about how oxygen is always -2, but if it's in a peroxide, this would be the only time where oxygen has a -1 oxidation state. So for example, like hydrogen peroxide, notice, right, this is again a special peroxide bonding, so that refers to like a oxygen-oxygen bond anytime you have a peroxide. And so that's a little special. So the entire O2 is -2, meaning each oxygen, right, is a -1. So that's only peroxide, so that's the only exception. So I'll put peroxides, oxygen is -1. Otherwise, always -2. And that's just important because we usually base the oxidation state off of oxygen, especially with like metal oxides. So we always want to ground ourselves with oxygen. And so I mentioned sulfate, so that you'll see a lot. So SO4 2-. Some chromates and dichromates. Phosphate is also common. And so you may want to make a little note because you have all of these, right, are all anions. So they're all negative except for these 2 down here. So that's just something kind of to keep in mind, right? Most polyatomics are negative, and then ammonium is one of your few positive ones, and then you have mercury, which I usually don't really consider a polyatomic. So usually it's just ammonium. Let's see. I want to say take a minute or so to go through this. So polyatomic. Let me go print out a chart, though. I think that'll be more helpful, because you'll probably want one. All right, I'll be right back. I think I have some copies in my office. That'll be much more helpful. All right, I have some in my office. I'm making more copies. I'll give it one to another share. Right now, I'm just handing out enough to kind of share. Then I'll come back around and make sure everybody has one. All right, I'll be back with more copies while you work on this.
That's not a question. I don't know how we've been doing it. Tomorrow I can't be with Kristen. He's a science teacher. Well, he told me about questions. We're gonna have a little lunch. Yeah, tomorrow.
All right, get into it. What's up? What's up?
Oh, I'm lost.
Well, right, because so then you got to break it down a little. So this, right, is still our normal cation, right? That's still just potassium. But then you want to find, right, what's this polyatomic?
Dichromate?
Yeah.
Where did you get that from? On the sheet. You had to look really hard for my numbers. Is this like a complete list?
For the most part, yeah. I won't hand you anything that's not on that list on the exam. So the first one, yeah.
Where's, I don't see a CR. CR207, got it.
So people kind of said the first one, so I'll at least write it. So, right, you have to do kind of some hunting, some identifying. We'll give people more time to mull over that.
What's supposed to say? I don't know why it's not. But I think it's just too.
Yeah, we're just naming.
Oh, okay, so
Yeah.
we're not doing,
Yeah.
Well, these should still be neutral, right?
yeah,
It's just that we got to write their names. But this one, we're just kind of identifying.
OH2, there's an OH on here.
Yeah, so then there's OH, right? And then there's just two of them, is all that's saying.
So does that change what we call it?
No, you still just call it hydroxide.
Magnesium hydroxide. Why is the OH in parentheses?
Since it's like one unit, so that you recognize it as a polyatomic hydroxide.
I got confused.
So what do we get for this next one, MgOH2? So magnesium hydroxide. And so excellent, right? So you just want to identify, so this is my normal cation there, so that's fine. And then my OH, that's my polyatomic. And so you probably found, right, hydroxide up here. And then notice, right, they wrote the formula all balanced, so hydroxide, the whole thing has a -1 charge. So that's why they put two of them, so that this whole hydroxide, right, balances out the magnesium. So again, you're thinking about, well, I have my magnesium cation, and then we could draw out what a hydroxide would look like. So, right, there's two little hydroxides then hanging out next to it. What about this last one? What do we get?
Iron nitrate.
But what do we need for iron? So what's the problem with iron? Where does it fall? Right, it's a transition metal. So what do we say about transition metals? What about the oxidation states? Those always apply. So we're just writing the names, right? But so look back at our nitrate. And so, right, so first we want to recognize, well, this is iron, so this is a metal with multiple oxidation states. So that means, well, I got to specify whatever the heck the oxidation state is. So what's the oxidation state of iron? And we can go back to nitrate, right? So nitrate, that's NO3, -1. So it's -1. We could do our reverse swap trick. It still works, right? So FeNO3, there's 3. If we do reverse swap trick, 1 negative, 3 plus, well, that works, right? Because -1 matches the charge of nitrate that's on there. It's -1. So then what should I write for my iron nitrate? What oxidation state? 3. So iron 3 nitrate. And so right, if it was iron 2 nitrate, so what would that be? So iron 2 nitrate. So I would start off, we write Fe, we can write nitrate, NO3, right, -1. And then we need 2 from our 2 here, so then we can write our 2. So I was doing a swap trick, and I'll rewrite it prettier. So iron 2 nitrate. Are we okay with this? Do we need some more practice, or?
Yes, please.
So let's try to see if you can write the formula. So tungsten 6 phosphate. Tungsten is W. And then, sorry, I'm still trying to figure lead 4. Let's just do azide.
I don't know what's going on. Can you start bringing those? I think that's, yeah, I just want to know when you win that.
Yeah, this is 6.
It's been a while. It's been like since 6th grade since I dealt with Roman.
Oh my gosh.
What is the second one after that?
Azide.
Writing down numbers and hoping he's right.
So let's start with this tungsten 6 phosphate. So how could you approach this? How could you write the formula? What do we get? There's a couple of different approaches. So let's just start with the swap trick, right? So tungsten, it says it's 6, so that's 6 plus. And then phosphate, so that's PO4, 3 minus, right? And so if we do our basic swap trick, so this becomes the subscript there. And so if we rewrite this, we get tungsten 3, PO4, 6. But then what's the problem with this? What do we spot? What'd you guys say? What'd you say? They don't make 8?
Yeah, like they overflow the,
Oh. Well, that's that's because I'm not sure you're counting the electrons, because this is, but there's something else just like mathematically funny with this. Somebody said, yeah, so you can simplify it, right? So they have their greatest common multiple, so they both can be divided by 3. And so this is a good intermediate, but then, right, you want to recognize we could simplify it, so we get tungsten PO4 2. That's just phosphate, right? Because for phosphate, it should be this PO4 3 minus. So just make sure you're not looking at phosphite. And so you could have, right, approached it through other ways. So you could try to set up your algebra. So 0 is equal to 6 times your number of tungstens plus phosphate, so -3. But I think the swap trick kind of works out nicely. Are we all okay with this? What's wrong? Everything can't be wrong though. So does the swap trick make sense?
None of it makes sense. I think getting the numbers to put in the swap trick, at least for mine.
So the numbers, right, but the numbers just come, so they either come from our chart, right, if they're polyatomics, we're just reading that negative sign. And then in this case, we were given, right, in the name that it's 6. Yeah. This 3? So that's when we do the swap trick. So then we swap them, right? So the 3, just solving for the algebra, 6 for the phosphate, but then we can reduce it to simplify it. And so setting up the algebra formally may help some people, but... All right, try lead azide. What do we get for the formula? All right, let's hear the guess. Excellent. Is this what we got for lead for azide?
How did it? I thought it was 2 on the outside of the parentheses.
So this one was a little tricky. So azide, right, if we look at what that is, so that's N3 with a -1. Then we have lead is 4 plus. So we could maybe just see, well, if I have a 4 plus and a -1, I need 4 azides then to balance that out. So that could be one way. We can, of course, still do our swap trick. So again, right, this is 4 for lead, azide, just from my chart. So again, this one doesn't have it, but this chart has azide, right? So azide, so -1, and then we can do our swap trick. So 1 and 4 there. All right, let's do some more practice. Okay. The good thing is that this is what this chapter is about. So let's do these 4, but we haven't gone over this one. So just see if you can name them. There's no crying in here.
There might be soon.
Molybdenum.
Yep.
Although chemists usually just say Molly for short. Not to be confused with Molly, though, ecstasy.
I don't know how to say this. What'd you say? Huh? Go on, do it.
Okay, what's the other part?
SO4. Well, we're just trying to name it. You want to go further.
Well, to name it, you have to figure out the
Or two. One more bigger one. Thousands? Easy one? Is that TIS? Oh. Oh, I TL. Idiot. Just sometimes. Just sometimes.
So that's like halfway there, but then we just check our oxidation state to more than those. Yeah, they're the same. So this is right, sulfate, this is SO4, and then so that would be -2. We have to do it. So then we can do -2 times 3, that gives us -6, and then that's probably +6.
No, I'm just gonna ask if it would be titanium free nitrate. Is that what it is?
So the 3 is still down there.
No, but there's a 3 in the middle. 3 in the middle. I'm doing the thing. There's a 3 in the middle. Because look, there's a 1 on the outside, there's a 3 right there. So this one right there. That's me using my Mr. Master tools. But I'm close.
You are very
Good enough for me.
Good enough for government.
Yeah, because what you're trying to do is.
So is there a 3 in the middle?
Algebra, so this is going up there.
So am I right? The 6 on top there. So the 6 is
And one minus, but then right, sulfate is not negative one. And so that's why I say that's fine, multiply everything by 2 now, that's -2. That's
why.
+6.
There's a 2 because look at your sheet.
Is it in the upper right corner?
No,
I whipped it.
I think the second one.
other sheet.
So it's been whipped out. At the bottom. Negative 2, yeah.
Has a charge of -6. And so when you do this,
So do I just put a 2 in the middle?
watch.
So whatever that is, 6. Oh, the second one.
Okay.
You put that -3.
I know, I got
6
I got the same
next to
thing.
that SO4, but you can simplify. So 2 and 6.
I don't understand how.
Imagine like fractions. If you're 2 6.
Yeah, so let's, all right, let's do number 1 together. So what do we get for our answer? How do we approach this? There's a couple of different ways. Do we have answer ideas or how we got there? Yeah, the first one.
I liked mine a bit better.
Thoughts? So wait, what do we know about this SO4? What can you tell me about it? So it's sulfate. So I'll at least write sulfate. And then what's the charge on sulfate? I'm going to write some scratch words. So it's -2, and I just want to write that down. So SO4 -2, you don't have to. So there's a few different ways to approach this, right? So we have however many sulfates there are. We know it's -2. We can see there's one molybdenum. So you could set up the algebra, right? 0 equals whatever oxidation state of molybdenum is plus 3 times -2, right? So this is for the sulfate. So then what would you get for the oxidation state of molybdenum? So 6. So this is one way to do it. So you could do the swap trick, so that's why I wrote it out like this. And so let's do that. So this is a 3, this is a 1. Reverse it back. So this is 3 plus, this is 1 minus. But then this is where you go, oh, well, that doesn't match, right? Sulfate is not -1, it's 2, but that's fine. Multiply everything by 2 so it matches, right? And so now we get 6 plus and 2 negative, and that's, again, our answer there with the swap trick method.
Why did you complicate it so much? He didn't.
Does that make sense for everybody?
So you still would find it on the periodic table and then try to match it here.
Well, you want to base, because right, this metal, it could be any oxidation state. So that's why I'm not necessarily looking at the periodic table, but instead we want to base it off of the sulfate, right? And so we know sulfate's -2, and then we know there's 3 from the formula. So that's how we can get a +6 for molybdenum. What about this next one? Are we ready for number 2 here? Okay, I think I heard titanium, 3 nitrate. So this one, again, I would either approach this algebraically, so you know nitrate is -1, so -1 times 3 is -3. We only have 1 titanium, so that's 3 plus. And right, we could use our swap trick again, so 3. So back it out, so that's -1, that's 3 plus, and yes, nitrate is indeed -1, so that's fine, that algebra works out, so that looks good there. Now, what about this next one? How do we name it? Oh, it's just the H though. So sodium. And what's the ending then? So what's our naming rule, right? We just changed the ending to "ide." So what is that? Ah, you keep putting in hydroxide. Right, hydroxide. This. So what's this?
Oh, that's OH.
Did someone say hydride? Yeah, so it's just sodium hydride.
There's no number?
Nope, so remember, sodium is your group 1, so this is always going to be in the 1 plus oxidation state, so we don't need to put any Roman numerals or anything. So what about this one? Can you at least name this, and then we'll go over the water thing. Should be on beryllium. And then what's the last part? Sulfite? Fight, thank you. So sulfite. The waters are.
Yeah.
And so we didn't go over this yet. And so how we name it is, so we'll go, kind of the last bit of this chapter is kind of hodgepodge. And so we want to name water molecules. And so sometimes you have this weird hemi abbreviation. So this would be if you have like one water molecule in between two other ones. But then otherwise we just use these prefixes. So we had 7, so we're at hepta. And then we just put the ending as hydrate. So yeah, we'll go back to this one. Oops, if I can find it. And so beryllium sulfate, heptahydrate is that last part. So it's just whatever your number prefixes and then hydrates.
Where does the hepta come from?
The hepta is just, yeah, the 7. So going back to your usual prefixes. And so we didn't quite go over it. So
Where can I find that?
it should be in the notes. I think it should be in your textbook somewhere. But otherwise, if you just look up like common prefixes, right? So mono's 1, di, tri, tetra, penta, hexa, hepta, octa, nono, deca. Those are pretty common. So let's do some more practice. Let's do the other way. So let's try these 4. So see if you can write the formulas now.
Arsenide is not on the list.
So it may be an element then. Yeah, that's just arsenic.
There's an arsenite.
V. Yep, V. No, yes. Five, yeah. I think. No.
I don't think arsenite was on the chart. Arsenate and arsenite.
So then it might be an element.
Oh. Sorry, didn't click.
No, those are the ones people usually miss the most are nitride, arsenide, and phosphide. No, it's the element. Everyone's tricked by arsenide.
Yeah, so
Just solve it.
I
That's the goal.
Yeah, that really helps.
You're welcome. two different courses. Oh wait, that's just phosphorus.
Oh, sorry, question.
What? Check.
Oh, no, you're fine. Crazy. Yeah, never mind, you're good. All right, let's go over them. What do we get for the first one? Vanadium 5 arsenide. Someone want to give me the formula? What do we get?
I got VAS5.
Wait, what'd you get?
I got VAS5.
I think we're missing something. Oops, and I put the wrong. Because what'd you get for, you didn't get any subscript after vanadium? So I would expect, yeah, 3 after vanadium, and then what'd you put after arsenide? So that will be balanced, but let's go through it, right, because we have to make sure that it's balanced. And so I think the easiest way with this is to use a swap trick, so we could do V and AS, and so, right, we're told it was 5, so I'll put a 5 there. And then, right, arsenide, so all these, I don't know why this is, but just historically, like arsenide, phosphide, and nitride, students always confuse these, so just kind of be aware of this. You see that "ide," right, it's an element. And then, so it's -3. And so it's easiest to do the swap trick. So we get 3 and 5, right? So we just want to make sure we're balancing it. And then double check yourself, right? Arsenic is -3, so -3 times 5 is -15. We said vanadium is +5, so +5 times 3 is +15. So you just want to make sure you're writing, right, a neutral compound when you do these. So what about the next one? Let's try that. What do people get?
So it would be CO, and then parentheses, and then NO2, and then close the parentheses, 3.
Yep, so that looks pretty good. And again, we could use our swap trick, so cobalt 3+, and then nitrite NO2 -1. And so, right, we just swap those, so 1 and 3, and that works out pretty nicely. Excellent. What about this next one? We have yttrium perchlorate.
YCl04.
And then do we need some balancing or something? So what oxidation state is yttrium in?
3.
3. So then, what do I need to do to balance? Because these perchlorates from our chart, it's -1. So then what do we need to do to balance that? What do you say, put a 3? Yeah, so we need a 3 on the perchlorate. And again, right, we could write out our work, so ClO, 4, -1, yttrium is 3+. And then we could just do our swap trick to give us our 1 and 3 there. What about the last one? So silver phosphide.
AG3.
Yep, so that looks good. So once again, right, we have our phosphide, so don't let that confuse you. And so silver's always 1+, and we do our swap there. How are we feeling about this? So we have like 8 minutes left of class. I figure we could just do some more practice, or if you just want some like alone time to look at your homework and I can answer questions, we could do that. Would you want to do some examples, or do you want some time? More examples? Which way do you want to go? Do you want to do this one or the bottom one? This way? Okay. So let's practice writing. So let's try to do these next ones in our remaining time. So 5 through 7, or 5 through 8, see if you can name them. Yeah. Yeah, if you gotta go, you can sneak out, it's fine.
That's when I was confused with the first one I got it on. So what you need to figure out first is what here. And
Oh, nice.
That's phosphate.
So write that out.
So what am I writing? So you figured out what it is. So you have iron, tin, that's what that is. Okay.
Because it's not just normal iron. And then you already figure out what this is before, which is the phosphate.
So
So that's what it is. You have iron.
I think it's
Oh, okay.
phosphate has a negative 3 charge, so you take all of the 6
What? For 5?
Yeah. Is it? No?
I would start with the reverse swap trick.
It's iron 2 phosphate.
That was right.
Thanks,
Oh, yeah, you can put it in that. So let's go over 5. So right, we have this FE3, PO4. And so I would start with our reverse swap trick. So if we do them in reverse, right, we get 2 plus and 3 negative. Well, 3 negative, right, that matches with phosphate, so that's probably a good sign. And so I'm expecting iron 2, and again, just double check yourself, right? So it's if iron is 2 plus, so 2 times 3 is plus 6, and then negative 3 on this phosphate times 2 is also negative 6. So yes, iron 2 phosphate. Does that make sense for that one?
Yes.
Have you gotten 6, or do you need more time?
Is 6?
And you give us this, or like a.
Well, remember, look at your funny ones, and what?
Is it nihonium? Is that how you say it?
Ammonium?
No. NH.
Yeah, NH is ammonium, NH4. So this is a weird one because it's 2 polyatomic. So you have your polyatomic cation and your polyatomic anion.
Wait, so is there 2 NHs on the periodic table?
And you're looking for a
So this whole
polyatomic.
thing, that whole thing is not in both of them.
Oh, both of them are
Yeah,
going to
'cause there's 2
Got
of them.
Ammonium.
I heard ammonium, so that's a good start. Yeah, ammonium acetate. And that one was, the trickiest part is identifying the acetate.
Okay, so all you have to do is identify it, there's no like special switch that you can just.
Yeah, so you're looking like, okay, there's no metals with multiple oxidation states. And then you can separate them into cation, anion, and then you're like, wait, they're both polyatomic. So then you're just naming them.
Is the test open now?
Yeah, the test is open now.
And if I have the sheets, cool.
Then what do we get for 7?
Dihydrogen phosphate.
So we got half of that.
So it'd be vanadium dihydrogen phosphate.
But then we need, so what's the problem with vanadium?
Four, vanadium. 4.
Yeah, so we have to specify since it's a multi-metal, so exactly.
This is down here.
Yeah, you can turn everything in there.
Vanadium.
Let me just do this last one. And then let's do, what about this last one as a class? What do you get for this one? So you could do reverse swap tricks, so negative 3, 7 plus.
Do you have to write the number in Roman numerals?
Then you would have to do manganic phosphate. So it's much better to write it in Roman
So I'm
numerals.
going to have to learn my Roman numerals.
Yes.
How many should we study up on? Because I think I know up to like 5
I
off
know
the top of my head. So should I study like
Wait,
1
is
to
it-
20 or?
IV, is that 4? Or is it VI?
I don't remember the switch because one's 4 and 6.
Yeah.
So IV is 4 and VI is 6.
See, I'm just gonna write it on the inside of my notebook, but I need to know how far up to.
Probably up to 10 is reasonable.
Up to 10.
We usually only do like 6, but
Got it.
this is right, manganese 7.
Yeah. Oh.
Phosphate.
But that one makes sense because 7.
Oh, I just wrote it in lowercase, right? Because I could have done VII, and that's the same thing. I think you already grabbed that because that was all from lab. So as long as you already picked up the homework, you did the lab. Huh?
Where would I pick it up?
You
Is
should have
that- Is
got
that one of the things you gave to me? or-
it was out in lab, so if you grabbed it,
Did.
okay, then grab it.
Okay.
Okay, now,
Wait, both of these?
one of them is a lab packet, so you did do.